I'm James. I reckon a lot of new faces here, so hello, nice to meet you all. I am currently a NERC research fellow based in the maths department. I also hold a proleptic lectureship, which means that once my fellowship expires at the start of 2016, I will become a lecturer, which is nice to have that. And my PhDs in an environmental science kind of background, and really specialising in meteorology and climatology. In terms of my research interests, I guess if there was one underpinning theme that rides through everything at the moment, it is the Arctic sea ice. Now, when I say the sea ice, which is kind of visualised in this plot here, this is a thin layer of ice that forms from freezing of the Arctic Ocean, freezing seawater, so it's ice that's floating on top of the ocean. It's typically like 1 or 2 meters thick, in contrast to the continental ice over here on Greenland is much thicker, and it forms through snowfall and accumulation of snowfall. So I'm not really going to talk at all about the ice sheets on Greenland. What I'm really interested in is this floating ice, which waxes and wanes through the annual cycle. This has come out quite small, but this effectively shows the cycle of the sea ice. So it grows in the winter, and in the summer it melts away. But we still retain a fair amount in the summer. It doesn't completely melt, and the colours are really bad here. But the top line there is the kind of the long-term average based on about 35 years of satellite data we have, and the coloured lines, which are all plotting below, show what's happened in the last 6 years. So we can see that and this has been well documented, you may well know, that this ice is melting at a really rapid pace, particularly the summer ice. The amount of ice that remains in the summer, which is down here, is considerably lower than it was 30 years ago. And this is a kind of time series of effectively the amount of ice that exists at that summer minimum. And it's been dropping like a stone. And some particularly really record lows, first of all, that happened in 2007, and then surpassed by quite a long way in 2012. So this is a kind of really iconic aspect of recent climate change. So connected to this issue of the melting sea ice is what's been termed in the literature Arctic amplification. Effectively what that is saying is that the rate of warming in the Arctic has been 2 to 4 times faster than the rate of warming over the globe as a whole. So this map here shows annual mean temperature trends over, I think, the past 50 years or something from the IPCC report. And it just shows this real bullseye of much strong warming over the high latitude northern hemisphere, over the Arctic. And that's projected to continue into the future in climate models run with increasing greenhouse gas concentrations. So this is a phenomenon of observed and projected climate change. And a lot of my work has been looking at kind of what's driving this, the processes that are going on, the feedbacks, of which the loss of sea ice is one of them. So if you have large warming, you melt the sea ice, that has a feedback to the ice albedo effect, and that generates larger warming. But actually it's not quite as simple as that. There's a whole bunch of other feedbacks and processes which I'm not going to get into, but I've done a fair amount of work looking at this and trying to understand why the Arctic is warming so rapidly. One aspect of this has been to do model experiments. In the real world, it's quite hard to tease apart all these multiple processes that are kind of acting at the same time, and there's forcings, there's feedbacks, there's interconnected processes. So one way to go with this is to go kind of more idealized sense. You take a climate model and you perturb the sea ice in some way that you want to examine, and then you look how the climate responds. In that controlled way, if you're only just changing the sea ice, then you can really isolate what's going on and what role the sea ice has in the climate system. So I've done a fair amount of work on this over the past few years, and that continues at the moment, doing these kind of idealized experiments. And I'm trying to summarize maybe 2 or 3 papers in one kind of cartoon here. Effectively, what happens is, so here we say this is a part of the Arctic Ocean. And it was ice covered. If you remove the ice cover to first order, the first thing you do is you change the albedo of the surface. So where you had a relatively bright white surface, you now have a kind of a darker ocean surface. So that means you absorb more of the solar insolation, which means you warm the top layer of the ocean surface. Now, what tends to happen is that heat kind of accumulates in the summer whilst the sun is high, melting more ice, and then as you proceed into autumn and the atmosphere starts to cool, this heat that's trapped in the ocean then gets released to the atmosphere and drives warming in the low levels of the atmosphere. And not only are you transferring heat, you're also transferring moisture, so you're increasing evaporation, so you can increase your cloud cover and your precipitation. And also there's a tendency to get change not just the total amount of precipitation, but the phase in which it occurs. So as you're warming, you're going to get more rain and less snow, and that also has a feedback back onto the albedo via how much snow you have on your sea ice cover. So the whole complex processes that go on when you change the ice in it. But this is pretty much focused here, and this work is pretty much focused on the things that were happening locally in the Arctic. So in the vicinity of the regions that were losing the sea ice. But an interesting dimension that this work has taken now, and where I'm really going with this, is to look beyond the Arctic and to say, well, okay, what are the potential impacts for us, for the mid-latitudes, for other regions? Because there's reasons to believe that as you change the large-scale temperature gradients at the surface of the Earth, you can have an impact on the large-scale atmospheric circulation and the kind of things that drive our weather patterns in regions outside the Arctic. And some of this is a real hot topic at the moment, and it's been picked up not just by scientists, but the media and everything. So every time we have a extreme event now, whether it be a cold winter or a wet summer, these headlines appear blaming it on the melting sea ice or the warming Arctic. And kind of, so really, the point of that's in the background of when I was writing the proposal for my NERC fellowship, which I've got, fortunately, and it is titled Arctic Climate Change and its Mid-Latitude Impact. So this is the broad overreaching goal of this work, which I'm one year into the 3-year project. And this is how I pitched it to the NERC, to improve our understanding of Arctic climate change and its impacts on weather and climate in the mid-latitudes, and of the physical processes that govern these interactions. And this is a joint, I have my partners at the Met Office here in Exeter, and also at NCAR, which is the National Center for Atmospheric Research in Colorado in the US. Just see how much time we've got. I'm going to skip over that. So I'm 1 year into this project now, and it's going all right, I think. We've have 4 papers out already from this. I haven't got time to talk about all of these, but I really want to talk about just this one at the bottom, which provides kind of a nice application of the research I'm doing, and is also relevant to us, because it's about Europe and it's about UK weather. So you will probably all remember some of our recent summers have been rather disappointing, wet, cloudy, lack of sunshine. So these maps come from 2 particularly bad, if you want to frame it like that, bad summers for us. Summer 2007 and summer 2012, and these are from the Met Office, and they're effectively showing precipitation, so rainfall anomalies over the 3-month period, June, July, August. And you can see in both these summers, the blue colours are intuitively meaning wet here. The UK was pretty washed out, wet, horrible. This happened, summer 2012 happened to be my first summer back in the UK after living in Australia for 3 years, so this was a particular kick in the teeth. And so there was 2012 especially was this kind of the summer that never was, as people were saying. It was not only wet, this map here is sunshine hours, which were very low, and temperatures were cooler than average. But it's not just been just these 2 events. In fact, if we go back, so these are now maps for well, I haven't got the latest one on here, but the 6 summers, 2007 to 2012, so that's the 2 I've just shown, but 2008, 2009 were also wet. 2010 and 11 weren't so much, but averaged over the UK, they were still wetter than average. So it's kind of, you're starting to wonder now, is there something going on here? Is this, rather than just being a couple of random anomalies, is there actually something other than natural variability going on? It can take that in a slightly longer context. So here what I'm plotting is a record of precipitation for England and Wales that goes back right to the turn of the century. Again, blue is wetter than average and brown is dry. And you can see, well, there's a lot of variability in this. But within this record, summer 2012 was the wettest since 1912. So it's not unprecedented, but very unusual. Summer 2007 was the second wettest since that year. The 5-year period here is wetter than, that's shown by the black line, is wetter than any other. And yeah, so again, it's showing this picture of it, these being very, not unprecedented, but very rare events. But what is unprecedented is that at no point in the record do we see 6 years in a row that were wetter than average, apart from this recent period. And you can look at that over a slightly wider domain, rather than just looking at, in the UK, this here is now averaged over this region of northwest Europe, shown by the box. And this recent period stands out even more obviously if you take northwest Europe as a whole. The record doesn't go back as far, but still we've had this kind of apparent increase in the last 6 years. And again, some of these unusual years stand out in a European context as well as the UK. So going back to I'm saying Arctic sea ice runs through a theme through all of this. Hypothetically, hand waving, we can go back to this plot of the evolution of Arctic sea ice and see, okay, so the 2 records were 2007 and 2012, which also happens to be the 2 years that were really wet. Now, of course, correlation doesn't mean causation, but it's kind of worth looking at. So this is what we set out to do, and I was saying we did this by means of running some model experiments whereby cause and effect can be established. So the idea here is to take the atmospheric components of a climate model, and you run one scenario where you have more ice, and then you run another scenario where you have less ice. And then you run these for a long period of time to get a good sample of all the natural variability in the climate system, and then you compare kind of the average of all the long run with the high ice and the average of the long run with the low ice. And if we just look at the differences, and these are the differences in the sea ice in those runs, you can see that obviously in the low ice run, by definition, we've got less ice. Red colours here mean less ice, warmer, effectively. And these by design, these patterns were chosen to represent the trends that have happened in the real world over the past 30 years. So if we backtrack just one step and say, okay, well, what are the drivers of these wet conditions in the UK? So what I did here was to take the average precipitation over this box and compare cases when it was very wet and very dry. So the 5% wettest cases and the 5% driest cases. And what's shown here is effectively the winds at about 10 kilometers in the atmosphere, which define or can be used to mark the jet stream. So presumably you're all familiar with the jet stream. It's a narrow band of strong winds high in the atmosphere that tends to steer our weather systems across the Atlantic and then bring us our rain effectively. So what we have here is in the wet conditions, we see that the jet stream and you can kind of think also this is the storm track is located quite far south, and the hits Western Europe, and in the dry years it tends to be further north, which means all the storms go up here and miss the UK rather than whacking straight into us. This is based on observations. If you do the same kind of analysis in the model, you see very similar things. So what's driving the precipitation variability in observations in the model is a similar thing, which is reassuring. So then with the model, what we were then able to do was say, okay, now let's compare. Well, this is just basically showing that it shifts south, wet versus dry. But if you're then comparing the model with the case with the low ice versus the high ice, and this is plotted in the sense that it's the anomalies corresponding to Arctic sea ice loss and the melting of ice. You see that this is again these winds high in the atmosphere, but now in an anomalies rather than the raw values. So what this is showing is the jet stream is shifting south in these model runs as you remove the ice. And this is in the model what happens to the precipitation. We see wet conditions over northwest Europe. And if we compare, so going back, this is what was observed over the last 6 summers, and this is what the model produces. There's a pretty good agreement here in the spatial patterns. I didn't point out earlier, but when we've been wet, actually the Mediterranean has been uncharacteristically dry, and the model picks out that and a few of these other features. The only thing to mention here is that the magnitude of these, I didn't put the colour scales on, but I've got some numbers down here. This is effectively a third of that, so potentially up to a third of the trend, or could, according to these model runs, be caused by the loss of sea ice. And I will just leave that up there, and I'll just stop there and take any questions.
Thank you very much.
Thank you.